Hey everybody, before we jump into the details of this problem, let's just work a concrete example for a number that we can actually write down. Let's look at 135. Now 135 is equal to 5 times 3 cubed. And just by its form alone, that's 27, 5 times 27, I believe, cubed, right? So 5 times 27 is 135. So 135 has exactly one perfect cube factor, namely 27, right? So the answer for that would be just trivially 1, right? But we want to do it for this huge number that we never would be able to calculate by hand. Find the number of perfect cube factors / divisors of 3 factorial, which is an easy enough number to calculate. That's 6, but then you get 7 factorial, and you're multiplying that times 11 factorial. Now, a perfect cube has the form some integer raised to the 3n power. Notice that right here, this would be 3 raised to the 3 raised to the 3 to the first power, right? Or 3 times 1, I guess. But in any event, this is the general form of a perfect cube integer. It's I raised to 3 times some natural number, and I should write n is greater than or equal to 0, where that's a non-negative integer, okay? Now, so since perfect cubes have this form, it makes sense to determine the prime factorization of these larger numbers. 3 factorial is just 2 times 3, so we don't have to mess with that too much. We will take that into account, but the hardest part, I guess, or the tedious part is to find out what the prime factorizations of 11 factorial. Now there's something called Legendre's formula, and I'm going to go through that. I'm going to show you how we found 3 to the 4th. The way that's done, and you would take 11 here, which is, I guess, the base. So we're talking about the floor function. That's the greatest inner function of 11 over 3. Okay, and then you would have to run up and do the floor of 11 over 3 squared. Now the reason why is because 3 squared just got counted once. 3 squared is a multiple of 3, so you see this ends up being 3 right here, but it counted 3 squared because 3 squared is a multiple of 3, but there's still one more, right? Now this is 9, so this is 1. Okay. Now there is a terminate condition on this Legendre formula thing. You do the floor of the next highest power, which would be 11 over 3 cubed. Now notice this number is between 0 and 1. This number right here, well, it's 11 over 27 between 0 and 1, so it has a floor of actually 0. So these things are always guaranteed to terminate, right? So notice we have 3 plus 1, which is the 4 that you see right there, okay? And you would do something similar for all these. And a lot of these you can just kind of see almost visually, without having to write all this down. But this formally takes care of business right here, and I did double check these things, okay? So 7 factorial has this prime factorization, 11 factorial has this prime factorization, utilizing this process. All right, now, so now I said adding the respective exponents. Now notice now I'm including 3 factorial because it's just 2 times 3. This part right here is just 2 times 3, and we've already seen what 7 factorial and 11 factorial are. And so we add all the exponents up, and this is what we get for our product without having the faintest clue how this would be expressed in Hindu Arabic, the decimal expansion, the 10 attic, or whatever they call it. Okay, so you got this huge number, but it's expressed solely in terms of the canonical prime factorization. All right, now that we have this canonical prime factorization, we can utilize the fact that this would be a general cube given 2, 3, and 5. Notice that 7 and 11 don't count here because they never can have a perfect cube with 7 or 13, 11 here based on the exponents aren't big enough, right? So combinatorically, you could write it in with 0, I guess, exponents or something like that. But it's not important. This is the form of a general perfect cube for our number based on our prime factorization of the object we're trying to find the number of perfect cubes for. Okay, now, one thing to pay attention to right now is A can take on the values. I'll just write A right under here. So A can take on the values 0 That would be okay, because if a were 0, you would just have a 1 here, but this part would still be a perfect cube, right? This is a little like the famous result number theory, where you have to allow for 0 as an exponent to account for the factors of 1, okay? Now, also it could be 1 because you could have 2 cubed, 2 because you could have 2 to the 6, 3 all the way out to 4, right? Now, why did I go all the way out to 4? Well, simply because 13, is greater than 12, and 4 times 3 is 12, right? Now let's take a look at 3. How far can we go with for our b variable? Okay. Well, again, 0 is always going to be a possibility if this gets left out and the rest of it is a perfect cube, right? So we got 0 here, and we can just go up to 2 here. Okay. So note that we have 5 possibilities right here for exponents, and we have 3 possibilities for the exponents right here. Now, how about 5? Well, 5 is not much fun. For the c variable, we can only take on a value of 0 and 1. So there's 2 possibilities. Now, notice there would be 1 possibility for these other 2's, but these other 2 bases, that would be 0, 7 to the 0, 11 to the 0. But it's really ridiculous to even write that down, in my opinion, okay? So what we have right here is 5 possibilities right here, times the 3 possibilities for the exponents right here, and then times the 2 possibilities for the exponents for the base 5 condition. So what I'm getting is 30, okay, equals 30. There's 30 possible perfect cube factors for this unpronounceable number, which is somewhere in the trillion range, I think. So it's 30. Now, also, you could ask the question, what is the biggest one? Okay, what is the biggest one? Well, you can write down the biggest one fairly quickly. It would just be 3 to the 12th, right? Times 3 to the 6th. And this is the biggest one, folks. It's not the question that was asked. It could have been a separate video if you want to take it that far. But notice that this would be equal to 3 to the 4th times, oh, God, that should be 2 right here, folks. Sorry. 2. Okay, and this should be 2 to the 4th right here. Sorry. 2 to the 4th. 3 squared times 5. Quantity cubed, right? Quantity cubed. Now, can we do this math in our heads here? Let's see. So that's a cube. If you want to know that this is actually small enough to figure out, this would be 16 times 9 is 144, and 144 times 5 is what? 720? And so this would be equal to 720 cubed. So we did, this is the largest. This would be the maximum, okay, cube. This would be the maximum perfect cubed. And by the way, this is in the trillions, I think, this number here. I think it exceeds, it's past 100 billion, I think, and I think it's in the trillions, this number. So again, none of us by hand could ever even write down or calculate the Hindu Arabic or the base 10 version of this, but there's no need to with this beautiful object called the prime factorization, okay? So again, the answer is 30. Let me know what you thought.